Okay, so here we're going to be doing an example of Dijkstra's algorithm. So we're given this graph on the right here, and we are given the starting vertex A, so this one, and we need to perform Dijkstra's algorithm starting from node A. So just remember from lecture that Dijkstra's algorithm is it creates what's called a shortest paths tree. So it's single source, so the single source is A, and multi-destination. And all the destinations are D, E, C, B, basically just all the other nodes in the graph. So after the result of Dijkstra's algorithm, you'll be able to know, first of all, what is the cost of the shortest path from A to whatever node. And by cost, I mean, so I think for E, it's you go to B, and then you go to C, and then you go to E. So that's the shortest path there, and that cost is 7 because it's the 4 plus the 2 plus the 1. So you need sort of labels on your edges here. In this case, they're integers, but they could easily be decimals or basically they could be decimals. We'll see later on that there is a condition that you need to have on these labels, but we'll talk about that once we get to part B. Okay, so that's what Dijkstra's algorithm will do at the end. You'll be able to figure out the shortest path, or the cost of the shortest path, as well as the actual path, because if you want, for example, if you want to know the way to get to E, it doesn't really help knowing what the cost of that path is. You actually want to know from A, what are the steps I do? So you will have we'll encode that information so that afterwards you'll know, okay, if I want to get to E, the shortest way is to go to B, and then to go to C, and then to go to E. We'll see that later. We'll see how that works. So, okay, there's not really enough space here, so I have the pseudocode from lecture kind of pasted here along with the graph and a whole blank page. So let's write out the different data structures. Before we do that, actually, I first want to note that it's pretty similar to the other graph traversals we've done, meaning BFS and DFS, because you have this fringe here. And in Dijkstra's algorithm, the fringe is a priority queue, but in the other traversals, it's something a little bit more simple. So it's a stack in the case of DFS, and then a queue in the case of BFS. So this one's a little bit more complicated, but it's still the same kind of idea, where you're putting things on the fringe, and then removing things from the fringe, one at a time, and then you have this similar while the fringe is not empty condition. Well, actually, in Dijkstra's, you don't really the fringe. You never add to the fringe, but you do modify the fringe in some cases. So we'll see an example of that when we go through here. So let's just initialize our data structure. Or we'll need an extra one that's not here, which is the edge2 array. So let's start with the priority queue. So initially they're all, let's see, yeah, so the vertices are A through E. Let me write those. A, B, C. Okay. And initially, so they're ordered by smallest distance, where distance, we'll call it dist2. This is like an array, so you'll need to somehow encode each of these vertices or nodes as a number. So A at index 0, B at index 1, and so on. The actual order doesn't matter too much as long as it's consistent. And the third data structure you'll need to actually reproduce, how do you spell this? To actually reproduce the path is an edge2 array. And it's not too complicated how that works. Okay, so it's the same as dist2 in the sense that it's just an array. Dist2 though is an array of integers because the values here are integers. Like this one would be 0, this one might eventually be something like 2, and so on. But in edge2, it's an array of vertices. So this is saying from E. So if I want to know the path from from A ... to E, then you can use this edge2 array to kind of work backwards. So So to know where from E, where do I go? Sorry, where did I come from? You'd follow the edge to. So in this case, it should be C. That just happens to be what the best node to go through is. And then from C, where do I come from? In this case, it should be B. And then from B, where do I come from? And in this case, it should be A. And then A doesn't really come from anywhere, right? Because we're starting from A. So we can put like a value like null here. So that's how the edge to array is used. It's basically where did you come from? Not where did you go to, but because where you should go to depends on what node you want to get to. For example, like for the node C, here, if I want to get to the node B, I shouldn't even go to C, right? Because from A, I can go directly to B. So if you're at C, you shouldn't. I don't think there might not even be a way to get to B from C. So that's kind of why it's like why it is like the way that it is. It's like where'd you come from, not where did you where are you going to. If that is confusing, then when we update it, I think it'll make a little bit more sense. But initially, these are all like empty. The dist2 array will store. So actually, let's like annotate that. So it's like where you came from. And then this is shortest known distance from A. Remember that for Dijkstra's, you need to start at somewhere. So it's always from a single node or a single vertex. So the one value we can actually put in dist2 is the one for A, and it's just 0. Because from A, if you want to get to A, you just don't go anywhere. You're already there. So just 0. And then all the other ones, you can initialize to some really big number. Kind of like how if you want to know like the minimum value in an array, you might have like a min variable and set that to like infinity initially, and then update it as you go. So we'll do that here. We'll put infinities. Okay. And that's basically doing this part right here. So for each node, set the distance to infinity, and set the back. In this case, they call it back, but here we're calling it edge2. So we'll set them all to null. And note that only A will stay null because A does not come from anything because it's the starting vertex. Okay, where are we now? Okay, the fringe we're adding everything by in order, like with the priority being dist2. So the priority here, actually we don't really need to put these in this pseudocode here. We're kind of assuming that these node objects have like a these node objects have a attribute dist instead of dist being like a external like separate array, and that internally, like the way you compare two different nodes is you compare their dist instance variable. In this case, we have a separate array, which is totally fine. Actually, I will keep those there actually. So the priority that I write in the priority queue is going to be exactly a copy of whatever is in dist2. So the value for here example is going to be the same as the value there. So just infinity. So let's fill those in. A0, everything else is infinity. Okay, so a little bit of duplicate work there, but should not matter. Okay, and then now we just carry on in the loop. So we're going to pop and I'll make a note. I'll make a cur variable here so we know which one we're at. This corresponds to V, but I like to call it cur because it's like the current one. Okay, so we're going to pop A off. So A gets popped off because A has the smallest priority. So A gets popped off. And now we're going to do this process of relaxing the edges. So, okay, this got a little cut off. So what relaxing means in Dijkstra's algorithm is from the current node, which is A, we're going to see, we're going to try and update the successors of A to see if maybe we found a better path than there to get there. So for example, in this case, it's not really going to do anything interesting because we don't even know how to get to B yet, or D. So the values there, the dist2 is infinity. So basically this comparison you do here, is the distance to, the distance to its successor, which is w in this case. So the w right now corresponds to b. So let me write that, infinity. And we're going to compare that to the distance to v, where in this case v is a, because that's the one we popped off. So the distance to a, that's just 0, plus the distance from a to b, which is this edge weight, right? And that's 4. And we're going to compare those two numbers. So infinity, which is the previously best known shortest distance from a to b, which is infinity because we don't know a distance yet, compared to this new way to get to b through a, which has a cost of 4. And since we want to know the shortest path, we're going to take the smaller of those two. Since the smaller one is 4, we're going to update the distance. So that's basically now, because that's the smallest thing, we're going to do all these updates here. So the first update is changing the distance of b. So here I'm going to change it here to 4, and because I wrote with the separate dist2 array, I'll change it here. So if you did not have a dist instance variable in your vertex class or node class, then you would actually need to update the priority queue. So there's like a method of priority queues called, I think, update priority or something like that, where you give it the object and then you give it the new priority, and then it'll basically change that the priority in the queue here. So in this case, it'd look something like fringe dot, maybe it's just called update actually. I don't know. You'd have to look that up. Dot update b and 4. You just call that, and then that would update the fringe for you. And then you'd also need to do this adding to the dist2 array. Okay, but let's not get too much into the details. Okay, so we updated there, and then also we do this w.back equals v, except in this case, so in the pseudocode here, we're assuming there's like a back instance variable too. In this case, though, we just put in a separate array. It's totally valid, and we're going to update it right here. And this is kind of reflecting that we found a better way to get to b. Right now the previous edge 2 of b was null, but imagine it was something like non-trivial, like d. So maybe earlier we found a way to get to b, and let's say that path had a cost of 10. And so then this path is cost 4. So because it's better, we're going to update the priority queue in the dist2, and we're also going to update the edge 2, saying, okay, actually b, you should not come from d because that path costs more. So instead come from a because it's a smaller cost path. Okay, so that's it for b. Now we move on to the next successor of a, which is d, because it's an edge from a to d, and we do the same exact thing. So we're going to compare infinity to 0 plus 2, because the edge weight is 2 here, and obviously 2 is less than infinity, so we do the same thing. So d, all of these will get updated. So that's 2, this is a duplicate, just put 2 there, and d, edge 2 of d is a, because the best way to get to d is through a, is from a. Okay, so that's it for a. Whoops, actually I want that. Okay, now we can move on to the next node. So we're going to pop from the fringe, and the smallest one is d. So let's get rid of d there. D. And now we're going to relax the edges of d. So d has 2 edges. One of them is to b. So let's see what let's see if we relax the edge from d to b. So the previous best cost path to b was 4, right? So 4. And we're going to compare that. So this 4 kind of represents the w.dist in this condition here. And we're going to compare that to the distance from a to d, which is dist2 of d, plus the distance from d to b, which is the edge weight, right? It's the weight of from v to w. And that's 3 here. So we're comparing, so the distance from a to d is 2, and the distance from d to b is 3. And so in this case, so because 5 is greater than 4, it means that this is not a better way to get to b, because we can save an edge cost of 1 if we just go from a to b directly. So nothing gets updated here if condition is not satisfied. So we just move on to the next successor, which is C. And C has, see, we haven't even gotten C before, so it's automatically going to get updated. So let's update there, there, and there. So the edge cost is going to be 2, because that's the best cost from A to D, plus 4, because that's the cost from D to C. So 6. 6 there, 6 there, and D there. Okay, now we can go a little bit quicker. I think you probably have a handle on this now. So let's pop from the queue. 4 comes out. Oh, sorry, B comes out because it has priority 4. And let's try to relax the edges. We see this edge to C. So the current best way to get to C has a cost of 6. And if we went through B, it would have a cost of 4 plus 2, which is also 6. So we basically found an equivalent way to get to, or an equivalently good way of getting to C. So it doesn't matter if we went from B or from D, it's the same cost. So here, it's a less than, but it really could have been a less than or equal to. It doesn't matter. Because in terms of path cost, it's identical whether you do ABC or ADC, because it just costs 6 either way. So we could update it or we cannot. In this case, I'm just not going to update it. But note that even if you did update it, that'd be totally fine. Okay, so we're at B, right? So B had a successor of C. We dealt with that. Now we're going to look at the E successor. So E we haven't visited before, so that gets updated in the normal way. So the edge 2 is going to be B, because the current one is B. And the path is going to be 4 plus 4, so 8. So the first 4 is the 4 because that's the best cost to get from A to B, and the other 4 is because that's the edge weight from B to E. Okay, and that's it for that node. So we're going to pop from the queue, and we pop C out, because C has a smaller priority. Okay, and we relax the edges. There's only one edge. It's E. So let's check that condition. So the current best way to get to E has path cost 8. And if we went through C, it would be 6 plus 1. The 6 because that's the best way to get to C, and the 1 because that's the edge cost from C to E. And 7, and that we get 7 there, and 7 smaller than 8, so we do update it, right? So we do the inside of the if condition. So that means we update E here, here, and here. So 7, 7, and C, because that's the current node we're at. And that's it for C, because there's no other successors. Now we pop off E. Okay, and E has no outgoing edges, so it just doesn't do anything at all. And now the priority queue is empty, the fringe is empty, so we stop. Okay, so now our dis2 and our edge2 arrays are completed. Like they contain all the information necessary. I'm going to erase this stuff for recreating a shortest path or finding out the smallest cost path. So let's check that. Earlier we did the example of A to E. Let's do that here and see if it works. So someone wants to know what's the shortest path from A to E. So we work backwards, right? Because edge 2 tells us where did I come from. Okay, well from E, it says I should come from C, right? Okay, C. And from C, I come from D. Okay? And from D, I come from A. Okay, and let's check that. That path has a cost of A to D is 2, so that edge is 2. D to C is 4. And C to E is 1. So that gives me a total cost of 7, and the dis2 of E is also 7. Okay, so that worked out. And you can apply that to all the other nodes, and you'll find that it just works. Now, as for kind of like why does it work the way, like why does it do the what it does? It has to do with like I guess kind of special property of the graph that once we've relaxed an edge, once we pop from the priority queue, that kind of cements the fact that that's the best way to get to that vertex, and there's no better way. So it's kind of like a greedy algorithm here, because we're kind of passing the it's like a dynamic programming algorithm, because we're starting off with like a really, so the problem we have is kind of hard, right? Because, for example, if someone wants to know the shortest path from A to E, it's a little bit tricky, because there's just so many ways to get from A to E, because you can do like ADE, or you can do ABE, or ABCE, ABDE. There's just a lot of different ways. And so what we do is we solve an easier problem. Okay, what about A to A? Well, that's really easy, because it's just, you don't go anywhere. Okay, what about A to B? Right, there's only one edge, or B is like only one edge away from A. So there's less ways to go from A to B. So we solve that problem next. And if you recall, in our priority queue, B got popped off before, or actually first D got popped off, right? Because it had this dis2 of 2. So it gets popped off before B, because that's like the next closest vertex to A. And so the order of things that we pop from the priority queue is in increasing order of distance. So first D got popped off because it was the closest thing, and then B, and then C, and then finally E, because E is the furthest thing. So not a super formal way of describing it, but hopefully it made enough sense. Okay. So just remember that this is basically the product of Dijkstra's, these two arrays, or if you modified, in this case, like if your node object, or if your vertex object had the parameters like dist, and in this case it's called back, that also serves the same purpose, right? So the A vertex, or let's do a more interesting one. The C vertex might have dist, or will have dist equals 6, and back equals D, right? So that's just here and here. I think it's a little bit easier if you use the two arrays, because then you don't need to add things to your vertex class. So anyways, let's do the next problem. So it's just a quick question about Dijkstra's and what conditions we need. So what must be true about our graph in order to guarantee Dijkstra's will return the shortest path tree to every vertex? Draw an example of a graph that demonstrates why it might fail. So you may remember this from lecture, and if you don't, that's fine, but we need to have positive edge weights all across the graph. If we have negative edge weights, it doesn't necessarily mean that we'll get a wrong answer, but we definitely could. It breaks the guarantee that we have. So let me draw an example of that, why that's the case. So let's do a simple graph with just two nodes. So A, C, and B. And it'll be like that. So what Dijkstra's algorithm would do is, let's say, and we're starting from A. So it's going to, the next vertex it goes to is going to be whichever one has a shorter edge coming from A. Because remember, we go in order of distance from the starting node. So let's say this is 1, and that's 10. So Dijkstra's algorithm will look at those two, and because actually let's just draw what it would look like in the priority queue. So A is popped off, so it's not even in the priority queue. B would be a priority of 10, and C would be a priority of 1. And because 1's less than 10, C gets popped off. But what if this edge from B to C is negative 10? Then it's actually worth it to take this initial really big edge 10, because down the road the path will get smaller. So this kind of the invariant that we need in Dijkstra's is that a path, like if I have a path from A all the way to B, and let's say that costs like 10, in this case it does cost 10, but it could be any positive number, then we're assuming that from B to any other node like C, it's going to be, that whole path is going to be at least 10, and no less than 10. So basically you can think of is that the paths only get worse. They don't get better. And worse here means they get greater. And better meaning they get smaller. In this case, that's not true because there's a negative edge. So because that's negative, then this thing is no longer true, because even though from A to B is 10, from A to C, like going through B, is less than 10. And Dijkstra's algorithm relies on the fact that that's not the case. So because we have a condition like that in this graph, Dijkstra's algorithm would give us the wrong answer, because it would say we'd have something like our edge 2 would look like this. A would be null, B would be A, which is correct, but C would be A also. When in reality it should be B, right? Because the best way to get to C is to take the 10 edge, but because then that allows you to take the negative 10 edge. And maybe also just to sometimes I like making this like really big, just to showcase that it's a way better path than the A to C, but Dijkstra doesn't even get to see it, because it doesn't even think that the path would get the cost would get any smaller, but it does because it's a negative. Note that it's okay that if this was 0, edgeways can be 0, that's totally fine, because as long as it's greater than or equal to 10, that's what matters. It can equal 10, that's fine. So it's okay if that was 0, because then you can have something like that, right? And then maybe you think, oh, going through B is better, but it's not really better, it's just the same. Right? The edge weights are just the same. A to B to C is total cost of 1, and A to C is also cost of 1. So it doesn't matter which one we do there. But when it's negative, that's when it is an error, makes a difference. Okay, so this is like this is like probably the simplest graph you can draw for this. You just need 3 nodes, 3 edges, and then basically kind of have this like initial this edge that kind of looks really good because it's really small, and this other edge that's really big to kind of dissuade Dijkstra from going to B, but then having this edge here that's like super negative, or not super negative, but like at least a little negative, so that it ends up being better to go through there. So that's like the way to construct these example graphs. Okay, that's it for that one. And there's actually nothing else we need to assume about the graph in order for Dijkstra to return a correct shortest path tree. It could have as many edges as it wants. It could have cycles. As long as none of the edges are negative, then we'll be totally fine. And in fact, negative cycles are, if you combine those two things, the negativeness and the cycles, then you get really weird behavior. Like, for example, if I have the graph A, then B, then C, then A, kind of like the same graph I drew in the topological sort case, and we had negative 1, negative 1, negative 1. Or actually, they don't all need to be negative. Let's make this 1, just to make it the point clear. So initially, and if we're starting from A, right, we said that the dis2 of A was 0, right? Well, in this case, it can actually be better than 0, so less than 0. Do you see how you can kind of keep going in this cycle from A to B to C? And every time you complete one cycle, you get a net negative 1. So if you do the cycle 10 times, you'll get negative 1 times 10, so you'll get negative 10. And if you did the cycle 1,000 times, you'd get negative 1,000, and so on. So the more times you kind of race around in this cycle, the better and better your cost to A would be. So you'd get really weird behavior, and there's basically not really a good answer of what's the shortest path from A to A, because there's a negative cycle. So it just doesn't really make much sense. So that's a little bit of a weirder case than the negative one, but yeah. Okay, so that's it for B, and I think that's it. Yeah, so that's it for this discussion. We probably have Piazza threads for this. If you had a question on here, feel free to ask there. And yeah, good luck studying for the final.